but we just had this talk by Paulo Verissimo, and he mentioned you already. So, and the Brazilian community know you by your very remarkable contributions in the area, books, and since the ISE systems that we know you here. And you have been with us in the Brazilian symposium on computing network and distributed systems, and many other participations. So the stage is yours. Thank you very much to be with us. It's a great honor to have you with us. Thank you very much. So please.
Okay, so let me start my slides. And while I do that, I'm going to also tell you a story that Macedo knows very well, which is that indeed I did come to the area for a previous one of these events. It was wonderful. That was many years ago. And he introduced me then. But before he introduced me, first, he introduced a local percussion band, a group that was very, very good musicians, and they were singing and dancing. So they did this for 10 minutes, and the room gradually filled up. In fact, the whole room filled, and people were dancing and yelling. And then at some point, Macedo clapped his hands, the group went away, and he said, and now I will introduce Professor Birman, the same introduction that he just gave, but from way back then. And I've never had so many people run away from a talk of mine in my entire life. So it was a wonderful visit, though, and I remember it very well. And I hope that the attendees are enjoying this year's event as much as we enjoyed the event back then. Such a beautiful area, such wonderful music and people, and everything about the host and the setting was memorable. I will never forget that trip. So this time, though, I made Macedo promise that if there would be music, they would be after my talk, a reason to stay. So I'll tell you a little bit today about Vortex, which is a system that my research group is building here at Cornell University. And Vortex, as you can see from the title, is an architecture for accelerating machine learning inference and knowledge retrieval. So inference would be situations where we classify something or try to understand something, and the knowledge retrieval would be the stage in which a query is turned into a collection of relevant documents. And Vortex is an infrastructure that we've been building that serves, hosts machine learning code and tries to make these kinds of tasks faster. And in fact, has a strong connection to the interests of the LaSiD group, Professor Verissimo and Macedo, which revolve around concepts of time in distributed systems and machine learning. So machine learning, you might not think of as having a significant time dimension, but perhaps it does, because we just heard Professor Verissimo talking about AI in time critical settings. I'm going to argue that there are other dimensions of temporal logic, temporal properties that are also relevant, such as causality and consistency, which distributed systems people often think of in terms of time, of formalizations of time. And so in addition to talking about performance, which is one of my goals in Vortex, another interesting aspect, for me at least, is that Vortex tries to engage on these kinds of questions. So let me set the context, although in fact, Professor Verissimo's wonderful talk, I think also sets the context, frankly. So we have a trend now, and it's very established, that AI will enter into many, many settings. This is something that was given to me by Microsoft. I have colleagues there and I do some work with them. And they are involved in a project called FarmBeats. In Brazil, I think this would be quite interesting, actually. And they want to try to use machine learning tools to improve the job of managing very large farms, often dairy farms, which is the example given here, or cattle being raised for meat. So you have problems such as understanding how your land will be used in the coming summer. And in the example here, is a river. This is a hydration map in which blue represents mud or water. So you can see that some of the fields are very wet. And you might be worried about whether your cows will be able to use those fields. And that might actually impact the amount of food you have for them, where you have to purchase it. You could start to use satellite images as a way to try to understand hydration problems in the region. You might take an AI that can predict river depth and an AI that can predict weather patterns, and take those as inputs to historical AIs that have learned about the behavior of your animals over time, and from that begin to do intelligent inferences. And the same kinds of characteristics are found in many other ML systems. And we'll talk about what those characteristics are in 1 minute. But here's an example also from a picture at Microsoft, but this doesn't exist. This is something people would like to build. So here we have a young woman who's servicing some sort of equipment, and maybe it's a turbine, and is checking for vibration at the suggestion of the computing system. If you think about this, she obviously isn't running an AI in her goggles because it would be too hot and too heavy. So there must be a computing cluster nearby that's collecting data, telemetry from all these different sources, and in real time is able to guide her and interpret what's occurring. So it says, touch the wand to the red tube, and in real time it's able to say, yes, there's evidence of some kind of a seal which is cracking. Or a medical example where a doctor might say, as you raise your right arm, tell me when it starts to pinch or hurt. And perhaps this is an athlete from soccer games. He's injured his shoulder again. Normally the doctor knows how to treat this type of problem, but with somebody with so many old injuries, needs advice and asks the system, what prior experience do we have treating a person with 5 different, broken collarbones who now has a new nerve pinch? And you can again imagine that that would retrieve information from databases. People talk about retrieving data also in the context of what are called co-pilots. This is Microsoft's one, but there would be one for any system you like. And so these co-pilots plug into applications, but they do rapid queries of machine learned data collections. And so timing is important for a co-pilot to be useful. Timing matters for that doctor. Now, these AIs share a property, which is that they're really distributed systems, programs connected by communication. So just to give an example, if you have knowledge retrieval where you're trying to collect a set of documents to answer the doctor, those documents were first captured. They were broken into what are called chunks, meaning collections of like 3 lines that are apparently important places in the document. That's done using a transformer. Each chunk and the document itself are then typically transformed into a numerical representation called an embedding. An embedding might have 1,000 points in floating point, and that's again done by a type of transformer. We can then form point clusters out of the embeddings, and that now allows us to do queries using a hierarchical search where we take the query, we embed the query, and now we ask which cluster of document chunks is this closest to. Maybe there are 3 clusters, and then we can say, take a representative high-quality sample of nearest neighbor document chunks, eliminate duplicates, and use that to generate a prompt for the generative LLM. Each one of these would be a separate program or a separate module in a single address space, but perfectly capable of running separately with its own model, its own logic. And when people will tell you that an LLM has a billion, a gigabyte of model parameters, billions of model parameters, they're often adding up the submodels associated with these sub programs, these experts in some sense. So here are examples of little graphs that represent the kind of design I was talking about. On the top left, a system that might do simultaneous translation for the United Nations, for example. Somebody says something, translate it to various languages, and simultaneously display. Below it, an image reading pipeline for children. So here you've got images and it describes the image, but checks to make sure that the language is appropriate for that age, and then produces an output. Top right, a question answer pipeline. The bottom left, bottom right is interesting. It's what's called a multimodal LLM. It actually has an image at the bottom, a second kind of mode of data having to do with depth at the top, and then it actually can answer questions about them. These are the kinds of things I want to tell you more about. And even the individual components can be distributed systems. This is just an example. I don't need to talk about it really. I took it simply because it illustrates an ML which itself was built to run as separate programs that talk to each other using a kind of a leader, scheduler, and worker model. A VLM would be an LLM that answers questions about images. So how do these differ from standard microservices, and how does supporting them differ? So machine learning systems today tend to be built by taking components and composing them together. You end up with a kind of a graphical program in which the nodes are the individual components and the edges represent the flow of data between the components. There's an ingress node, data arrives. There may be fan out because perhaps I got an image and a question about it. Then there could be parallel steps, and this could happen, it could be a very complicated graph. Nonetheless, most ML systems today are hosted, are served on a single server per instance. And we'll see examples of that later. What I'm going to show you is that it's not really a very efficient way to use the hardware, and that these kinds of observations lead to opportunities for us as systems researchers. They need to be elastic. On the other hand, if I simply run them on cloud microservice architectures, those assume very, very quick elasticity. I can add copies if I need them. I can drop them easily. Machine learning components have models that are really big. And if you try to launch an ML instance on a machine that isn't ready for it, you're going to have to wait 10, 20 seconds just for it to load its model. So there are big differences between microservices, and there are actually big differences between ML hosting and standard hosting as well. So standard hosting systems, model servers, actually do what I just mentioned before. They tend to take your entire AI application and run it on a single machine at a time, or on 20 machines, but as a single entity. Now, this isn't uniformly the case. There's a new generation of hosting infrastructures emerging that treat these as distributed computing problems. Ours is one of them, Vortex, but another example that's quite famous right now is RayServe. Another would be Inferline. And so my group is working in this new area, this emerging area, in which the question is, what is the best way to host ML applications, recognizing that they can be understood as componentized and treating them a lot like microservices, but not identically because of the big differences I mentioned. So it's one platform. And in fact, what's interesting is that we end up supporting not just AIs, which is a computational part, but even the data that the AIs run on. When you have programs which need these big models and are hard to move from place to place, we really ought to send our queries to the place the program is running. So this mindset changes the design and the way of solving problems, and we think in terms of sending requests to the data, really. The data includes the big ML models. And it turns out that this leads to what we call an extensible architecture. Vortex, because of this need to be able to host the ML models and other data, something called RAG databases would be another large category of data. And this need to send requests to the data, we end up saying we need a way to put the compute, the code, wherever the data is going to be. And so we co-locate data and compute. Vortex is built in 3 layers. So I'll tell you a little bit about the bottom 2 layers just right now. And then I'm going to switch and focus purely on the top layer. The lowest level is called derecho. It was a piece of work that we did over a long period of time that ended in 2019 with an ACM Talks paper, followed by another paper that came out in ICDCS on something called Spindle. And with the combination of that second piece of work and the Talks paper, derecho is the world's fastest solution for doing atomic multicast, Paxos-style data replication, distributed agreement, consensus, and quite a few other coordination and synchronization patterns. If it's possible, it runs on RDMA. If you don't have RDMA, it uses TCP. It's faster than anything you have ever read about. In fact, it's the first provably optimal version of the Paxos suite. Paxos is a family of protocols. Derecho is an instance of what people call Protocol 2 of vertical Paxos, also sometimes called virtually synchronous Paxos, which refers to a self-management model that I introduced and that Leslie Lamport later adopted when he did vertical Paxos. So vertical Paxos Protocol 2 is a specific Paxos instance. Derecho is very similar, but uses slightly different protocols that I designed, and it's faster. In fact, none of the prior Paxos protocols achieved optimality. We achieve optimality in several ways. Optimality in terms of the progress condition, optimality in terms of the delay until events occur. It's the smallest provably possible. It makes the most progress that is possible, again, provably. And we've used machine learned AIs to prove the properties of these protocols and to verify our proofs. So Cascade, the next layer, the middle layer, is an infrastructure for key value hosting built on top of derecho. We have a paper, we put it in the archive, but it's not actually published in a refereed setting. We were planning to finish it, but the lead author took a job at a hedge fund. And so I don't know if that will ever actually be fully finished and published. At any rate, you can read about it if you like. And then Vortex, the piece of work I'll tell you about today, adds in AI hosting and looks at the characteristics of these kinds of machine learning data flows under real-time pressure. All right, and then we have little pictures that I tend to use for each of them. A derecho is a type of straight line wind associated with hurricanes and tornadoes. Cascade is like water flowing down a waterfall, and Vortex is our newest. And the reason for this imagery is because these are all things where you shouldn't stand in the way. In our case, we shouldn't stand in the way of the data. You don't want delays. You don't want round trips. So you end up building your systems with zero copying, with maximum degree of hardware offload when that's possible, and asynchronous data exchanges. But you still need the strong properties that people used to talk about, and that my group has always talked about, and that we've found ways to map to that asynchronous model in our work on derecho, and Vortex inherits that. So the basic Vortex model is visible here. You have a service. It's running on a rack scale set of computers. It could be a larger number, but our experience so far is only at rack scale. In this example, we're supposed to be showing you 9 computers in little shards, subgroups of size 3 computers each. So the red circles are the computers. The yellow pages, they denote data that's held at that shard. And the idea is that a large data set consists of objects, they could be files. And in fact, we often prefer to use file path names as our keys for our model, our key value store model. And when files are put into this key value store, what we do is we shard by hashing the key, the file name, and that allows us to identify the shard that will handle the data, and then the shard fully replicates the data. And we have different versions. In memory, we'd use atomic multicast. Persistent would use Paxos logging. And the basic interface is key value get and put, which many AI systems support directly. We also have interfaces that allow us to pretend that this is Kafka, either in its DDS, which would be like atomic multicast, or its queuing behavior, and even its transactional behavior. And we also have a Linux file system built over it, a POSIX file system. Now, and I just mentioned for AI people that when you see KV, you should not confuse this with the QKV triples that arise in transformers. There's a connection, as it turns out, but our keys are path names, file names, and our values are collections of bytes. Okay, and QKV, they would all be tensors. Now, to extend Vortex, what you typically do is you take your machine learning code and you package it. We're going to support two ways of doing this. I'm going to tell you about the one that's currently done. And in this current version, your AI code is wrapped into what becomes a dynamically linked library, which is a standard feature supported in any programming language. And in fact, our code is in C++, but you can talk to it from Python, Java, C#, Julia, anything you like. They all have ways to outboard requests into C++ and vice versa. And so you take your code, you put our little wrapper around your code. It's very easy to do. And then you tell our servers to load this code. Now, which servers should load the code? It turns out that with machine learning, the code is not big. It's the models that are big. The models are a kind of data that the code loads. And so we just put that code everywhere. So every Vortex server, when it starts up, loads one or maybe even many DLLs. And here we see 3. And you can now start to think of the Vortex server as not being a key value storage system, but instead being an enlarged prompt formation AI or a smart result aggregator for some stage of one of these MLs. And the idea here is that you take the stages of the ML, the architecture, and you have one or more DLLs, and you install these extensions. And now, if I send a request to a particular shard, I can activate the corresponding DLL logic, and any data local to that shard will turn out to be local to this computation. So by being smart about data placement and data grouping, aggregating, and then by placing computations at the right shards, we can end up with co-located computation and very, very low delays. We won't have to move data from shard to shard. We'll be able to find everything we need at the same place. So each ML component is present everywhere, but not active. It's only active where we're actually using it. So let's take a concrete example that we're going to see a couple of times. This is just like the other MLs I showed you. This one has a user who asks a question about an image. The question has a text portion and it has a vision portion. The encodings, and by the way, these high dimensional encodings are the same space. It's really a concept space. So an image or a piece of text, they embed into the same space as high dimensional points. So the text encoder does the text side of the encoding, the vision encoder does vision encoding. If they're talking about the same thing, they should ideally come out close together in space. And then there's what's called a cross-attention module. And based on that, we have a collection of documents to look up, each represented, in fact, by another encoding, always these 1024 dimensional vectors, floating point numbers. So they're pretty big, 4K objects. And then this particular one is called a Colbert search, could be HNSW, it could be DiskANN. We're flexible about what the AI modules want to do in detail. We're going to host them just like an operating system hosts any kind of program you might want to run on it. Okay, so we're not telling you that we're going to offer one way of vision encoding. You're going to bring us the vision encoder you like best, and we're going to let you run it on Vortex. And there could be 5 vision encoders side by side. That would be fine with us. Here's another pipeline. This particular one is another document retrieval application, but it starts with audio, turns it into speech, does an encoding, does a hierarchical search, like I told you about before, clusters, and then a sampling of documents within the nearest clusters. And that document retrieval step then feeds into a generative step after checking for content that's inappropriate. And you could use this to support a person driving and asking a question in the car, and the AI comes back and gives an answer. The development process is not very complicated. You take an existing AI that you like and split it back into components. We've done that. Or you take foundation models and you combine them together and create a pipeline or a graph. You create a DLL out of the resulting system. You tell us how you want this mapped to the hardware, and now the components can hand tasks to each other through our trigger feature. Now, you could be thinking, oh, we should automate every step of that, but many of these steps involve application-specific knowledge, and when they are fully automated, which many other systems do, TorchServe, for example, the decisions are frequently very poor decisions. I'll show you some examples. By giving the developer an angle to advise us on what to do, we get much more quality. So a little bit more detail, but I have to be careful about time here. Started late and I'm going to run late, but I'm not going to run over. So the Vortex layer is a universal runtime. It runs on Linux, and Linux is available, but we're hoping that the DLLs talk to us, not to Linux. But they could do Linux system calls. It's offering this optimized pipeline support, and I'm going to show you the forms that takes. And its job is to ensure that we can place the stages on the hardware very efficiently, but we still have to obtain extremely high throughput because that's what's going to determine the cost of operating the system, and very low delays. And we want to use the minimum amount of hardware in order to still obtain that high throughput, which is an interesting scheduling optimization question. Okay, and then we also would like to support dynamically updating the underlying databases so that for people who are doing RAG LLM means retrieval augmented generative AI, people who are doing database extensions of LLMs can update the databases. So these UDLs are the name that we use for the nodes in the graphs, and each one of them lives inside some DLL. It's not necessarily a one-to-one mapping because Python, for example, requires that all the Python components are in a single Python address space if it's in a single program. So one UDL has to be for all of Python. This is because it uses something called the global interpreter lock. But if they weren't identical, then we could spread them over multiple DLLs. So now our goal is performance. So let's talk a little bit about what makes existing serving solutions slow. And by the way, I will show you how slow they are in just a moment. I'm going to switch from architecture to experiments in about three more slides. So here we have our doctor, and our doctor has a question for this AI computing system. And how does that work today? It could be on a cloud, or it could be on a private cluster. Probably medical data would have to be on a private cluster, but the software is similar. In fact, you can often use the cloud software on your own cluster. And so the image is actually captured by some device, and it would be uploaded to an image storage layer, a blob store, which is a special purpose file system or key value store, just for large objects based on images and videos. Then you could launch the AI that handles this question, and it would have to fetch the image. So there'd be a second transfer of that same image. And in fact, the storage system might have replicated it for fault tolerance. So maybe there were third or fourth transfer also. Once it's in the address space of this AI, the AI probably doesn't do computer vision in host compute. It probably uses a GPU accelerator for that. 3 transfers, this is going to be very slow. And actually, this is the first worry we have in Vortex. It's just a purely engineering concern. This is a bad way to engineer that solution. And in fact, it's very slow. So the data paths are not optimized for the right purpose. It turns out if you look at them, they're optimized for throughput, and they do pretty well from a throughput perspective. But because the AI platforms that exist today are really for batch machine learning training, they aren't such good choices for real-time support of hosting. And in fact, I'll show you that the doctor would end up seeing very noisy data. It's hard to support things that mix components from different languages because existing systems tend to be universally using a single platform. PyTorch is very common, for example. TensorFlow, also very common. You tend to build your whole application in one way. So these are the things we're going to try to fix. Now, in Vortex, how would the same thing look? In Vortex, we have a key value store, and then we have machine learning logic, but we've already learned that that logic is actually everywhere. And we have GPUs, but we've already learned that it's the same set of servers doing both roles. This is really the internal layer of Vortex, the middle one, and this over here is one of those DLLs. So what happens now if we focus on one of the servers is that, first of all, the server is exposing key value data to the AI logic, the lambda, through pointers. Key value interfaces don't copy, they use pointers, and that's very efficient. We can be secure if we're worried about that, although it's not a current focus of my project. We tend to trust these pieces of code. We can cache objects in places where they have a high importance. For example, we can cache the ML model on the GPU accelerators where we plan to run that model. In the configuration, they use the word hyperparameters, and the CUDA code that's going to run on the GPU. And now we can actually take advantage of hardware features that people usually don't take advantage of, such as RDMA direct, to move data straight from the source into the GPU. And now we'll be able to compute instantaneously on something which otherwise might have taken quite a long time. And how fast is instantaneous? Well, obviously these graphical models are going to have stages. Stage-to-stage delays in my system will be as low as 33 microseconds, millionths of a second. Stage-to-stage throughput as high as 4/5 of what the hardware could support. When I did an experiment with 100 gigabit networks, we observed, I should say 100 gigabits is 12.5 gigabytes. And we observed 8 gigabytes per second of transfer rate. If it was a 200 or a 400 gigabit network, these numbers would increase. Very fast. Now, is that a big speed up? We'll get there in a minute, okay? But I'm going to show you that it's a huge speed up compared to what happens today. I want to show you first the idea that strong properties that we have learned about for all of our lives in distributed computing apply in this setting as well. So I want to talk a little bit about data consistency. And I thought I would show you an example first and then tell you how we do it. So this is a real project that we did on the smart electric power grid. You'd like to monitor the power grid to detect instabilities like the one they had in Portugal and Spain recently. And you do this using a type of device called a synchrophaser, and you attach it to a bus. A power bus is one of the high tension wires. Here I'm showing the Northeast power grid of the United States. In the bottom is New York and Philadelphia, and up on the top right is Boston. And that's the group we worked with. And what they did was they deployed a large number of these synchrophasers and into the grid. Now, the grid isn't really a 20 by 20 grid or whatever I'll show you, but we'll think of it that way for simplicity. And we capture readings off of the grid in synchronized real time at 20 readings per second. They're small values, about 32 bytes. And then we can do things. We can make a visualization, or we can run an AI that detects an instability like they had in Spain. Now, here are visualizations, and what you're seeing are 3 versions of the exact same data, which represents actually an instability propagating through a grid. On the left, we've got our 20 by 20 grid of synchrophaser data, 400 separate streams of readings, one set of readings, one stream for each square. And you can see it looks like a mashup of some sort. It looks very noisy, except at the points where it pauses, right? But in continuous sense, it looks very noisy. I'm going to explain that this is because of the HDFS file system, the high level of errors that it produces. It's a standard part of machine learning. It's part of the Apache suite, Hadoop file system, but it doesn't work very well for this purpose. And then the middle and the right show two different configurations of Vortex. The middle one doesn't know how to find the GPS time synchronization data in the records, and the one on the right uses the data in the sensors. And you can see it's very clean at that point. So obviously garbage in, garbage out. If you're building an AI to control a power grid, you want the best quality representation of your data to be visible to the AI. If you expose the doctor or the power grid to noisy, corrupt data, it's not going to work very well. Or the doctor will say, throw this out. So how do we do that? Well, if you've taken Macedo's courses using Professor Verissimo's textbook, you've learned a lot about how we do that, and that's exactly how we're going to turn out to do it. Nothing new. We sharded our data. Remember, I told you about it before. So here's timelines. Up on top is old data. Going towards the bottom are new events. The events are arriving data through our put-get interface. There are lots and lots of synchrophasers or doctor activities or whatever. So each shard has many sources of data, but each object has a file name. The data is organized in a hierarchy, just like it normally would be. And sometimes these inputs trigger AIs, like in this case, a series of AIs to help the doctor by answering questions about the images. And so the AI might hit a first ingress node, but that might trigger two more layers, lambda 2 and lambda 3, and they might converge at some kind of action layer, lambda 4. And this is all happening while more data flows in. And this fundamental problem that HDFS was having was it didn't know which versions of the data to use for each individual piece of query, in particular because of running without coordination, and even when things talk about specific points in time, well, we have a clock synchronization bound. And so there may be multiple options even so. What we really would like is a consistent cut. And that's going to involve two aspects. One is waiting for a type of logical stabilization property to be achieved. Paxos does this, atomic multicast does this. And in fact, Vortex does this, but HDFS does not do this. So HDFS can try to respond to a read before the data is stable. So it's missing data and it returns the last value. HDFS also doesn't understand this concept of a consistent cut, which is an old idea from Manny Chandy and Leslie Lamport. Vortex does understand it, uses something called Kulkarni timestamps and a very simple, elegant algorithm for finding a consistent frontier. And it does it on data that's already stable and therefore is immutable and in a deterministic way. So if you issue the same queries again and again, you always get the same answer. And that's enough to give us the consistency properties I showed you in this animation before. So when we look at the picture on the right, all that we're seeing is that that aspect is in action. Picture on the left is what happens when you try to access data which is being dynamically updated and you query it before it's stable and you allow mashups to occur between things which are actually causally related, and it causes causal gaps in the past. So this is what we do, and it only takes about 50 microseconds for stability to be reached. So at the price of a 50 millionths of a second delay, HDFS could have actually offered consistency. But those people don't really care because they build AIs for ML training and are focused on throughput and offline batch processing. So what else can our community bring them? Well, we can actually bring them better performance. So let's talk about some important real applications, such as the health of your cows. We built an AI using a body condition scoring architecture, again, multimodal, multiple stages, running that AI on a standard Apache infrastructure using Apache Flink, which is the slow performance is the red bars here. It runs 10 times slower than when we run it on Vortex. In this picture, it says Cascade, but it's really Vortex. 10x speed up because of the architecture I showed you a moment ago. And it's true across many different system configurations. Here's another example. This is a lot like what Professor Verissimo was talking about. But I don't know if the UAE has intersections as busy as people have in places like Rio and Campinas and Sao Paulo. In my own intersection is from New York City. Now, the AI in this case, you can see it here. It has a green AI node which segments an image. Each moving object, we call it an agent. For each agent, we create a red AI that does projection of its trajectory, its movement. And for each data point that is projected, the blue AIs check for potential collisions. And you could use that to set up a check at an intersection. Is there anything about this intersection which is dangerous? And it would flag near miss events, hazards. There aren't any camels, but those would have been Fellow's version. The payoff is dramatic. Look at this. If we run this on our system, it runs nearly in real time. That's on the right. Within about 300 milliseconds after it's captured an image, it's fully processed it. So this is showing the number of agents on the y-axis up to 50, and then it's showing the amount of time to do the processing of each new captured frame. And it ends up taking about 300 milliseconds with a picture like that. You run the identical AI on Azure, takes seconds, almost 10 seconds. So something happens, and 10 seconds later, the system can show it to you. The doctor says, raise your arm, and then he has to say, hold still for 10 seconds. Remember I mentioned that we really are much faster? This is illustrating it. A lot of people learn to use Kafka. This is Kafka. In fact, it's an RDMA version of Kafka called Kafka Direct. So it's the best Kafka you can get. The left axis, the y-axis, is showing logarithmic scale, the delay in microseconds. Each big tick is a factor of 10. Here's Vortex in orange on 1 replica or 3 replicas. The circles represent the median latency, and these are the different sizes of objects, 1K by 16 or 256, 1 replica or 2. And then we put next to it in gray, Kafka on 1 replica or 3 replicas. Configured actually as a DDS, so this is not even Kafka with its queuing delays. This is Kafka running with multicast. It's a standard way you can configure Kafka. And what you can see is that Kafka, the medians are okay. We're faster, but not a lot faster, maybe a factor of 5. But that the tail latencies of Kafka are huge. Factor of 1,000 over here on the 16K side. And that's one reason Vortex is so much quicker. These are 2 of the AIs I showed you much, much earlier. One of them was had a picture of a person asking questions about a dog. That was actually pre-FLMR. It retrieves documents relevant to a query. And on the right, remember there was one with an audio microphone and doing simultaneous translations. Speech Sense is that type of an AI, and it's shown here on the right. And again, this one is showing throughput on different configurations. And what it's trying to show is that we can run with traditional model serving like torch serve. See, black is torch serve, and the throughput is very low. Or we can run on modern systems which support this componentized perspective. The one we compare against, the blue, is RayServe, which is the cutting edge, and the orange and red is Vortex. And you can see we're a little bit faster, not a lot, but a little bit faster. 2 different configurations, but now I'm going to show you there are cases where we're much faster. This is an instance of it. In the previous picture, we didn't allow Vortex to use RDMA. If you look at this picture here, you can actually see the Ray data in much more detail. The blue is Ray, And you can see now a 90% confidence interval with 5% above and 5% below. So 95% are the bar, and then there's a 5% outliers that we're not even showing you. And you can see the median. That's the dots, and we connected it. So you can see that as we present more and more load to the system, Ray is doing pretty well, and then starts to show a high variability of latencies. And you can see the actual values in milliseconds on the left axis. And eventually, Ray is obviously forming backlogs and micro-batching. Ray will automatically batch, opportunistically batch, and it starts to do that around 80 queries a second. So hopefully you understand that picture. And now you can see Vortex, same sort of picture, but notice that the spread is much tighter until we get to 100 queries a second. Now Vortex apparently hit its limits, can't get further, and big backlogs form and the latencies get large. And finally, on RDMA, and only Vortex supports that, Ray doesn't, we get very low, tight distributions. You can't even see the 95% range. And then gradually, we push much further out. You gradually start to see a spread of latencies. If what you care about is quality of service, you could pick a much more aggressive quality of service guarantee and still offer it at a much higher data rate using Vortex in combination with RDMA. And my very last experiment looks at those four examples I told you about before, but now we host them all on the same server, the same cluster. One of them, the green one down here that's got the big green bar on the bottom left, that has is multimodal. It has a vision step as well as a text step. Now, what these graphs show is how much different schedulers slow down the different applications in a job mix on a shared cluster. So you'd ideally hope that they would run at the same speed on an idle cluster. That would be 1.0, and any number bigger means that you've slowed things down. 2.9 is a threefold slowdown. Now, what are the different colors? The categories, first of all, are the different applications. They're all sharing the cluster, but we've split their experience out. Okay, so you've got 4 categories because we had 4 applications. And then the colors represent what scheduling discipline we used. We invented a new one called Navigator. Red is just-in-time, classic. H is another classic called heterogeneous earliest finishing time. And the orange is just hashing, random. And what this is showing is that depending on your choice of scheduler for clusters, you can have very, very unfair behavior, like the 60-fold slowdown that occurred for the visual task over here on the bottom right, on the bottom left. What's going on there turns out to be that we're under a heavy load, and the lighter weight tasks are finishing much faster. And we didn't have to do that. Look at how Vortex, which is on the left with Navigator, it only slowed it down by a factor of 1.8. And it's got a kind of consistent slowdown right across the line. So Vortex is actually doing quite a bit better. And the Navigator scheduler it's using needed half as much hardware to do that as the others. So we're saving money and giving much better properties. So I'm going to wrap up with that and take questions. It's a powerful framework. It's all open source. Big performance wins against a wide range of options. As we see ever more ambitious ML pipelines and data flow graphs, Vortex is the thing you would need. And I hope you'll consider using it. Let me mention the team, which grows all the time. But currently the leader is Alicia Yang. She's just superb, and it's her vision. And Weijia Song built Cascade. He's the one who left to join the hedge fund. And then TC Wan is an AI expert for us. Ben Landrum knows a tremendous amount about indexing structures for reg LLMs. And I could go on and tell you more about the others. We've had very generous industry funding, and I'm lucky I don't have any federal funding, so my project didn't just get shut down. So with that, let me take questions.
Thank you very much, Ken, for the excellent and clear talk. And it's really impressive, the speed up you achieved with Vortex, and also very interesting to see this definitions like global states and consistent cuts. being redefined in this context as well. Very interesting. So we have time for questions, and I know we are a little bit pushed by the next presentation, as Professor Deborah is already on backstage. And I'd like to make a question about this. So by your experience in developing Vortex, and do you think we need to redefine these concepts? Do you think there are new abstractions that are needed to face these scalability problems and of these distributed federated machine learning techniques? So what are the main lessons that you think are challenging distributed people designers, distributed system people designers with this new reality of machine learning? Also taking in consideration that we have real-time requirements sometimes that must be met, even if it's very fast, but sometimes it has to meet some specific timelines. And then how fault-tolerant systems can handle these kind of situations. Could you comment a little bit, please?
These are many questions. Thank you, Ms. Ada. They're very good questions. What I would say is that the situation today is so basic. The things we learned when I first met Professor Verissimo and first met you 20, 30, 40 years ago are actually important and valuable and surprising to the ML people. They work with PyTorch and TensorFlow, and they're not aware of the infrastructures they're running on. And we hear about a car crashing into a camel or into an elderly lady in Florida, and nobody points out that the image from the dashboard cam is not what the AI saw. And nobody tells us what the AI saw. So the infrastructure could easily be causing problems. In the case of the power grid, I know it was causing problems. And we know how to fix these with ideas that Paolo put in his textbook 40 years ago. And they are as valid as they today as ever. The question you ask about real time versus soft forms of quality of service, I would say the AIs mostly need quality of service. But they do bring new problems anyway, because more and more these AIs, in order to have acceptable performance and acceptable electric power and heating impacts, we need to map them to hardware. And this distributed mapping requires knowledge from the developers, but the developers don't really understand computer architecture. So I think a very big challenge right now is to learn to capture things that the developer knows about these applications, but that the system at runtime will not be able to figure out, and how to use that knowledge at runtime in order to effectively use our hardware. But beyond that, I believe there are going to be new foundational questions also, because many of the AIs are operating with an inherently probabilistic character. And yet we would like a strong semantic statement about the system. So for example, if I use an ML to assist a surgeon or to assist an air traffic controller, some aspects of that have strong logical consistency constraints, and yet some components are introducing probabilistic statements. And I don't think we yet know how to do, for example, a co-algebra that would be able to give us a strong semantic for this kind of mixture of probabilistic behavior, deterministic behavior, dynamicism that can arise because of elasticity on a shared platform. We don't know how to keep private data private. Everything I showed you is wide open to a malicious DLL. So we have to trust all the DLLs, but that's not a satisfactory answer. Ultimately, you'd like privacy guarantees. And I think that we're going to see a very rich new generation of distributed systems research questions emerging. They won't be centered on Paxos and consistency. We have optimal solutions. If you want that, use derecho. But there'll be a new generation and a new kind of distributed, and especially when we start to see cooperation between robot agents, for example, or wide area AIs with what they call agents, agentic AI. Remember all the issues with transactions having orphans, and how Barbara Liskov had this famous protocol that had to kill orphans, which people made many bad jokes about. Well, we're going to have similar problems with agents that were based on some belief, wandering the world and doing very strange things. So,
thank you, Ken. We have a question from the audience, local audience, please.
Of course.
Hi, Ken. Can you hear me well?
Can I hear you well? No, but I can hear you.
All right. So I hope this is better now. I have a question that is something I didn't understand very well on my end, and it is how do we handle scalability for a single service in the sense like I've saw a lot of illustrations of Vortex as being a set of service, and I know that we are mapping different models to the same vectorial space. But what I would like to know in the infrastructure domain is in the usual microservice pattern, we would handle individually, the scalability for servers as the load for that given server is increasing. And my question is, how is that implemented in Vortex? Is this any different than usual microservice, or is this just as usual microservice?
It's quite a good question. Alicia Yang is the leader of the subgroup of ours doing scheduling work, but there's a lot of interesting scheduling questions. Even in the initial work we're doing, we're finding interesting opportunities. The issue that arises for a system like RayServe or TorchServe is that it's not able to predict how big objects will be, how long they will compute, and how frequently different components will get accessed. I think a developer can shape these things if we give them the proper way to express themselves. But that then opens the door to a kind of new kind of scheduling focused on bin packing, where you ask how many instances of a given stage are really needed to get optimal behavior end to end. And Alicia has been showing examples where in these pipelines, some stages are very quick to compute, some are very slow, some need a big GPU footprint, others can operate with a small slice of the GPU. And by knowledge of this, she can identify layout patterns which are much, much more efficient. So there's a really interesting opportunity for people, I guess, with your interests of scheduling. They're quite dynamic, and with multi-tenancy, where you have multiple pipelines sharing the same cluster, they're going to be very hard problems. But I think that the value of solving them is that we'll see much, much better utilization of the hardware. And in a world where we're reading all the time about how AIs are using all the power in the world, we can cut those numbers by a factor of 100 or more. And we read about that with DeepSeek. The same kinds of opportunities occur here. And the same sorts of savings are possible, 100-fold savings. So it's an excellent question, and I hope you'll work on it.
Thank you. So we thank you very much, Ken Birman, for being with us. It's a great honor for us to have you here for our celebration of 30 years of our laboratory. And thank you very much for you, and I hope to see you someday in the future.
Next time I will come in person. So thank you for the invitation, and to everyone in the audience, have a wonderful time. And now you can bring the dancers out if you like.
Yes, after the presentation, we have something. Thank you.